Hello, everyone. I'm Professor Paulo Butzen from Federal University of Rio Grande do Sul. I'm here to introduce the last CASS talk of the year. We have the pleasure to have here Roberta Burger from Infineon. Now I would like to present Professor Altamiro Suzin, that will be the chair of this session. Professor Suzin, the word is with you. Thank you, Roberta, for being here.
My pleasure.
Thank you, Paulo. I have the pleasure to present our former student, Roberta Burger. It's a big pleasure to me. Good afternoon, good morning, good night, everybody. Roberta Burger has graduated in electrical engineering in '96 from University of Rio Grande do Sul. She has dedicated his career to the industry, working for key worldwide players in semiconductor industry like ST Microelectronics, Intel, Infineon, in field of memory, mobile, PMIC, and automotive applications. She has accumulated more than 20 years of digital and analog design development, between others, RISC microprocessor, SAR ADCs, audio amplifier, DC-DC converters, and since 2015 has been contributing to the development of IMS SoC motor control, bridge drivers, and power distribution for automotive applications. Roberta, it's a great pleasure to have you here. Please, the floor is with you.
Thank you, Professor Sozin. It's also a great pleasure being here. Thanks for the invitation. I'm really, really happy. So hello to all. I'll be talking today about some challenges we have in Presilicon verification of analog mixed signal products for automotive applications. I'll start with a motivation while present then what kind of products I'll be handling in this presentation. I'll bring some important aspects about Presilicon verification. I'll bring some statistics to you, and I'll talk about some state-of-the-art techniques we do employ and why it helps us. And especially considering this audience, the impact of a broader knowledge in the work of verification. And then I'll close with a conclusion. As a motivation, I can think of at least 3 good reasons why to invest in Presilicon verification. It is known that the efforts for Presilicon verification has been increasing steadily because the products are getting more complex with more features and higher levels of integration. So if we can reduce this cost, would be great. Second, automotive specifically has one of the most stringent quality standards, and it impacts not only the hardware itself, but also the whole process under which it is developed. And last but not least, we are interested in developing economically viable products, and reaching a high quality first silicon is a decisive factor on boosting the profitability of the product and ensure time to market. In all these 3 aspects, the Presilicon verification is a key part of it. What kind of products I'll be considering in this presentation? They're typically all the ones electrical parts that goes into the body part of an automobile. And we can separate them in 3 classes. The first one is power distribution and protection. We call them intelligent switches because we have some features associated to it. Then we have the motor control, and these are going to drive, let's say, the motors of air conditioning, heating, ventilator systems, and the power lift gate, and so on. And the third class, it would be the lighting, so interior, exterior, for safety reasons or comfort reasons. We have several challenges in automotive. First of all, we deliver more than 1 billion of pieces every year. In Infineon, we are known for having this zero defect mindset. And indeed, we have, let's say, passed from parts per million defects to parts per billion defects. The environment where our devices are built in is extremely harsh in terms of electrical, magnetic, mechanical, and also thermal stress. And the complexity of the components has been increasing also in terms of integration levels. On top of it, we have strong, let's say, characteristics typical from automotive. And the first one is the fail safety, which is represented by this ISO 26262. We have these trends of autonomous driving and electrification, and those three parameters are impacting directly our Presilicon verification. I'm going to spend more words about this in the next slides. And not only we have our, let's say, personal goal of continue receiving these awards from our customers in recognition of our excellent quality and support. So again, one of these trends is the safety, field safety. And this is represented by this ISO 26262. It's very well known for automotive market. And it is a collection of several hundreds, I believe something like 800 rules on how to handle the safety of an automotive application. And the first step is to define the ASIL level of a certain application in terms of automotive safety integrity level. We analyze the failure in terms of exposure, so the probability of happening, the severity and controllability we have over it. And we can then define several levels in A, B, C, and D. And D is the most strict one, let's say. Having that, we can then define or decide which kind of level we want for the system to have. And there are actually three ones. I'm going to mention only two. It could be fail safe. That means if a failure comes, the whole system is going to be brought into a very well predefined state. The second one would be fail operational. That means a failure comes, but the whole system is still available. How can we achieve this? With a special architecture, with several assumptions, and with a failure catalog that helps to classify the failure and propose countermeasure. The Presilicon verification is a key, let's say, part on this, because it is the one that brings the evidence that the system or the hardware we are building is compliant to this ISO. Another trend very, very well known is about autonomous driving. And to put in a different perspective, I find interesting to know that in Germany, we have about 30% fails on driver license car practical test. And what I find interesting is that here we have the perfect hardware. We have a brain, and we have the perfect sensorial capability. We can see, we can hear, and we can even smell if we want. We are subject to several hours, maybe hundreds of hours of deep learning, if you want. And nevertheless, it happens during this test that something was considered to be a threat to the security of others, and this person is considered to be inapt to drive. So it's not trivial. But anyway, we know it's going to be the solution will be a collaboration between hardware, software, and artificial intelligence. Infineon can help with this hardware. So we prepare components with high computational capability. It can sense the environment. It communicate among different parts. It is compliant to the ISO 26262. And very important, it uses a limited, reasonable, and sustainable amount of energy. Developing this hardware, of course, we cannot do without the Presilicon verification. The third trend or very important aspect is the electrification. So the goal is to lower emissions. Everybody has the same goal. We can do this in several ways. So we could, for example, substitute completely the combustion engine, but we can also help leave the combustion, but help, let's say, supporting the other loads we have in the car. And with this, we can increase the gas mileage. We can bring more performance and features into the system while reducing the CO2 emissions. So there are several solutions. Anyway, if this is the power distribution we had in the past, and the red dots are the components we had, so distributing the loads and also the power, with the new organization, let's say, of this power distribution network, considering only hybrid solutions, we have now a different placements of these products. We see that now the applications is different, and also the electrical characteristics under which it works is different. So this is impact enormously our work in the Presilicon verification as well. So automotive products, especially the ones that I mentioned before, they have very strong nature analog power. We are very interested in specific electrical parameters. We have to interface to the external world. We have to drive motors. So this is really the soul of the product. Nevertheless, with these new trends, autonomous driving, electrification, and fail safety, we need more features. We need diagnostic monitoring, configurability of the system, communication among the parts. And these are implemented in digital domain. So we have shifting steadily from pure analog to analog mixed signal. And we end up with a portfolio which is vast in terms of natures and integration levels. We have now products which is still pure analog. We have products mostly analog, and we have strongly mixed signal. So the presence of digital is very strong. And in terms of integration levels, we may have a simple gate driver, or also higher level integration with the embedded power. We have a microcontroller, for example, and we can communicate, and also the gate driver. The strategy of Presilicon verification needed for each of these products is going to differ immensely. So now considering specifically analog mixed signal products, what are the typical characteristics it has? The first thing that comes to my mind is the multiple supply voltages. So we have voltages for the high voltage, low voltage, dedicated to digital, dedicated to analog, or maybe a special mode, low supply, low power, or fail safety, for example. And this drawing here, it seems rather simple. Well, we see some dependency, but we don't see much complexity, let's say. But when we bring this into the chip, we may realize that it might be difficult to really ensure a proper analog integration, first of all, and a proper power up and power down sequence. So these dependencies, driving capability has to be everything perfect to work under our conditions. And this is what we have to face in the pre-silicon verification. A second aspect, it goes hand in hand with the multiple supply voltages, which is the multiple power states. And what I mean by that is that if we enable or disable certain supplies, we can create islands of functionality in our chip dedicated to certain functionality. For example, fail safety, the normal case, or low power, or even sleep, for example. And in this case, the challenge for the pre-silicon verification is to analyze and be sure that each transition from each mode under all circumstances is working perfectly. Another characteristic is already in the name. So we have analog mixed signal. That means we have crossing domains, analog and digital. And we need A to D's converters and D to A's converters. And if we get now several of them, we typically might run into problems of accuracy, performance, crosstalk between them, and we have to be sure that the whole performance of the system is still guaranteed, and this has to be checked in pre-silicon verification. Last but not least, as I mentioned before, we are still very strongly analog oriented, and deep analysis on all analog performance has to be done under all conditions that we have created now. Mm. So if we analyze the scope of Presilicon verification, the main one, I would say we have to prove a concept. So there has been a decision about the architecture to use. You want to ensure that everything works as predicted. We have to cover our functional verification. It is going to, the product is supposed to give a coverage. So the system might run into different status. We have to be sure that we have run into each of these states. Robustness against PVT variations, yield, mismatch. And last but not least, we have also to support the post-silicon findings. So if they have some bugs in the silicon, we have to reproduce what they saw because we have the observability and we can easier see what is happening, what is the bug. Now take into account these trends, let's say. When we consider autonomous driving, I would say it's just extending this region. Let's say we have more complexity, we have more features on it, and the area, let's say, is just extended. Instead, considering electrification, we have now multiple applications. So the same product might be applied at different applications. We have different conditions, electrical conditions, and also the power consumption suddenly is of very much interest. And the fail operational, let's say, case, we are going to inject some failure in the system. So shorts or cuts. So we are changing the hardware and analyze again that the system performs what it's supposed to perform under such situations. So when we work on defining a product, we usually go top down. We have a black box. We define what are the features we want, the functionality of the system. We break this down into different modules and break down again into different blocks. And we reach maybe analog and digital blocks. So it's very clearly a top-down approach. In verification flow, though, we go in opposite direction. So we first verify the block levels. Once we have some maturity, we can go up to the module level and only then to the SoC level. Each of these hardware levels have a very specific, let's say, goal. The block levels is where we are going to prove the architecture, what we thought about. We are going to investigate electrical parameters very in depth. We are going to ensure the basic functionality, the robustness and yield aspects, and probably we are going to investigate also the interface to external components. Once you are in the module level, though, you might be interested to see about configurability of this module, the controllability we have over it, the connectivity with these blocks or integration of the whole system, module functionality overall, and the coverage as well. And then again, at SoC level, we might be interested now in the programmability of the whole system, connectivity again, integration, system functionality, and coverage. If I had to guess where the biggest amount of bugs will happen, I would say the module level, because this is the first, let's say, level of complexity that the assumptions done during concept and development phase could have gone wrong and cause a bug in the system. If this is a sketch, let's say, a strategy of development of typical analogs or mostly analog products, we have here down the application engineering and concept engineering phase, so defining products. And we have now, we can recognize the three levels that I just mentioned. So the block levels, the module levels, and the top levels, the SoC levels. Associated to each of these design tasks, we have verification tasks. And overall, we can see the layout, the backend, the design phase and verification phase with our dependencies. So we can see this is basically the strategy of a certain product. If we want to verify a system, we need to represent it in different ways. And in Presilicon, we have basically three ways, not considering the prototyping, let's say, right now. The first one is a digital domain. So whatever analog macro we might have, we substitute by a behavioral model that describes the functionality of this analog. We build the system now fully functional. We have a certain good accuracy of the system in terms of functionality only. It is not enough for investigation of analog effects, but it is enough for the functionality. So the simulation time is extremely fast with the digital domain. Um, Also, the methodology they have is extremely powerful. They have randomization and lots of routines that can be applied. And we can reach here almost 100% coverage. And we can see in this sketch of the strategy, it is here mentioned, let's say. The second alternative would be having everything in the analog domain. And here we are going to work in the digital blocks and synthesize them, integrate in the whole system. And now we have everything in a netlist, which is the highest accuracy we could possibly get, not considering parasitics, of course. But the problem is the simulation time is extremely slow. It may take even weeks. So the coverage is going to be very low. We can run maybe a couple of simulations, not much more than this. And it is also represented here, let's say, these simulations. The third alternative is having a mixed signal domain. And in this case, we preserve, let's say, the analog domain into analog domain, digital in digital, and we use a simulator that is capable of um, um, crossing these domains. And here we get a good compromise in terms of accuracy of the representation of the system. It is enough also to investigate analog integration and debug it. And the simulation time is also good. So a matter of days might be with a good accuracy. Truth is that there is no one solution fits all. We have to think, or let's say, take the best of each of these representations and maximize the output while minimizing the effort invested on it. One particularity of our products, analog mixed signal, is that we have to go from one extreme, digital, to another extreme, analog. So we have to cover several aspects. So typically the functional coverage. So we have a set of requirements and we have to be sure that functionality is on place. Then considering digital, we have this connectivity and toggling check that's typically seeing that the modules has been well connected and the wiring between them has toggled at least once in simulation. Then we go to the block coverage, for example, in the RTL code. We want to be sure that each process we define has been hit at least once in a simulation. Then going towards analog world, we have to be sure the equivalence, ensure the equivalence between the analog, macro, and behavioral model we are creating, and that we bring enough information for the SOC verification level. Then we go really to electrical parameters, the typical analog investigations, and we can go even further. For example, analysis of a heat dissipation might be important if we have a specific component that is going to because produce so much heat that increases the temperature. And it could be dangerous if nearby there is a circuit, sensitive circuit, dedicated to fail safety, for example, that would be operating output of the outside operational conditions. So I listed here some aspects that might be interesting in Presilicon verification. And how do we organize this? The first thing is to define in which electrical domain you want to verify this. And we have three alternatives. I mentioned already the digital, mixed signal, or analog. Some of these aspects are going to be measured in more than one domain. And the second alternative we have is the hardware levels, at which hardware level we are going to investigate this. And typically we verified more than once, let's say in different hardware levels. This is the strategy of Presilicon verification. And here is a key decision that is going to maximize the output and minimize the effort. So considering now three hardware levels, as I mentioned before, so we have three person responsible. Actually, will be more because we have more modules, more blocks, but anyway, representative now. And if this is the graph of the hardware knowledge, let's say, and this is the time the people are going to work, there are some things important that I wanted to share. And the thing is that this activity here is usually split in two. There is the investment phase, what I call this orange bar. This is the time that this person needs to build up the knowledge about the system, about this block, and build up the test cases, the test bench, debug the system, um, build also the crosses or the checks that we want to implement. So then, after this is settled, we finally enter into this payback phase. This is when we are going really to effectively find bugs and fix them. I mentioned already the scope of each of these levels is different, so I'm not going to repeat myself. Um, we see two things. The investment phase, once we go up, it's much longer. It makes sense because these systems are much more complex. And another thing is that the knowledge of these person, they are overlapping to the next level by not much. And this person here might be very specific, might be have a very, very good understanding about a specific transistor, maybe in this analog block, but this person won't be really understanding the integration aspects of a module, for example. And this overlapping here is the common language between these two levels. We can see that this overlapping is not really vast normally. So if we analyze now a bug fix chart, when a bug happens, when this person at very top level finds a bug, the first thing that has it to do is to analyze it and see, is it within my core competence? Can I fix it by myself? Can I understand by myself? If the answer is why, yes, it's great. So the loop is very short. It might be no though. Then it has to contact the next person, the next contact level, hardware level. And then we have the same process. This person is going to analyze, is it within my core competence? And here things get complicated because, yes, of course, could be. Then the bug will be fixed quite fast, but it could go then down. It could go on the side because we have several modules, and it could even go up again if this person did a bad, let's say, conclusion. So this goes down until the last level, and we can see immediately then whenever we are going to cross these domains, either analog, digital, so lateral, let's say, or also the hardware levels, we are going to lose efficiency. And this is for very trivial reasons. First of all, availability of this person. So if this guy is in holiday is a tragedy. There is the lack of common knowledge. I told you already about this, let's say, small or very narrow overlapping language between them. Whenever we cross this domain, this person is supposed to reproduce again the error seen at a higher level and analyze it by itself. And then we have also the fix and try interaction that is going to take time. So if we see now the time we need to locate a bug, and here I mentioned 4 different verification domains. We have now block level, behavioral model against schematic. We have pure block digital, and we have the module level, which is typically mixed signal, and we have the SoC level. So these 4 different verification domains. Whenever we are in the block level, the time is very short to locate a bug, and a matter of hours could be located. Once we go to the module level, things get more complicated. If it is within this person's, let's say, core competence, it still could be a matter of hours. But if we go now down to a block level, it could take maybe even some days. And this problem or this time here really increases a lot once we go to the SoC level. It could take also several weeks to find a specific, I don't know, transistor that is out of saturation, for example. So, and here is a real statistic, let's say normalized, again, the same for verification domains. We see that effort per bug we have is really increasing almost exponentially once we change the hardware level. The reasons are clear now, right? We have the investment phase much longer, first of all, and the complexity of finding and fixing the bug is also increasing considerably once we go higher in the level of higher hardware level. So if we analyze this strategy and someone had an idea, why not relying in these levels here, removing this one, we can spare some money, because anyway, these guys are going to see these blocks. So you won't be surprised that I say that would give a damage effect for development cost, because we are going to pay much more for each bug that we fix, and also damaging effect for the time to market, because the time we need to find and fix the bugs is much, much higher. This is also statistics out of a product we did some time ago. And we see here the quarters, so the timeline of the project. And we still see the same 4 verification domains I mentioned before. And I consider it to be healthy. Why I say that? First of all, the findings at block level appeared very early on. So we could do this cleaning up effect for the rest of verification. As I predicted, indeed, the major number of bugs was found in the module level, and a very few bugs were found at a top level, let's say. So it's really well distributed. Also along the timeline, it seems the strategy was quite all right. So what are the state-of-the-art techniques we are using? First of all, we have a common language now for design verification. So in the past, typically the digital design was done in VHDL or Verilog, so VHDL mostly in Europe. But the verification now has been systematically been done in system Verilog because it's much more powerful. So we did have to create wrappers again, the modules here, and we had some troubles whenever the signals were crossing the, let's say, the simulated generation to the real RTL code. So bringing now the development of digital design to system Verilog, we have one single language, and we eliminate, let's say, one of the crossing domains or crossing worlds. The second aspect is using the same methodology, which is the UVM digital, to be applied in a module level and in a system level. And by doing so, we have to reuse, or you can reuse, the routines that were applied for system for this specific module at a system level with a very minor changes or adaptations. So the reusability here is boosted quite a lot. Then we have dedicated solutions for the ASU application that we have for fail safety. So we have methods of injecting failures and analyzing afterwards. We create behavioral models that are power aware and system aware. And I mean this system aware is bringing the special effects that might be interesting at SOC level verification. And we do use a formal verification at block level digital, which is a exhaustive proof that a set of properties holds against the design, a very low level, the block level. So with these techniques, we can indeed increase or let's say improve a lot the whole Presilicon verification tasks. Now, several quality aspects of a product nowadays can already be ensured by Presilicon verification methodologies, and I mentioned some aspects and also mentioned some techniques. There is one aspect, though, which is the analog integration robustness, which is very tricky. So because the pass-fail criteria for it is very subtle, it says only we are not supposed to have weaknesses in the system. And a weakness in this case is typically this strange or weird effect that we see in the lab. It happens only once a week, maybe. And it drags with it a group of engineers to analyze day and night during weeks, maybe, what is happening to the system. And it's very difficult to find the root cause for that. Finally, at the end, almost always. The problem is related to a very analog effect, like metastability in a comparator or a shoot-through current in a level shifter or a pulse, for example, in a voltage regulator doing power up. The best, let's say, way to address this issue is using the analog mixed signal verification with someone with a broader knowledge that understands the system, but also the very deep down analog performance, let's say. And for two reasons. First, if in simulations we see some kind of failure, this person would be capable of saying, yes, this happened because we have something happening this block level here, analog, which is causing this. So a pulse, for example, can cause a wrong power down, for example. And this information is very valuable because we shorten the time of debugging the system. But not only, it is even more important because even if we don't see this problem at SOC level, um, knowing that these effects could cause a failure in the system, we can actively look at them and prevent weaknesses in the system. And indeed, a graph here, I'm showing 4 different products using this methodology or this knowledge, let's say. And the gray bars represent the findings against the requirements, let's say. Everything was decided and that it was failing, really the system was failing. And these are noted here. The pink bars, though, they represent exactly the weaknesses only. So the effect was not strong enough to cause a failure in the system. Nevertheless, the effect was there, and maybe under different conditions, higher temperature or another corner, we would have run into a failure in the system. So I would say these pink bars here are really the decisive factor that we didn't have a redesign, let's say. In the same way, we can think that whoever is responsible for generating the analog behavioral models representing analog macros, for example, if this person knows that special effects from analog, like pulses, glitches, metastability, or delays, or something like this, could cause a problem in the SOC level, and this person brings this information into the behavioral model, we are increasing exceptionally the representation of the system. And when the digital domain is going to run simulations with this high number of simulations they have with highest coverage, the probability of finding real bugs is going to increase a lot. So as a conclusion, I can say the key of a good Presilicon strategy is finding a proper division of verification efforts among different domains and also different hardware levels. Whenever we can invest in these crossing domains, either analog, digital, or different hardware levels, and we can smooth the difference and let's say create a common language between it, it's going to increase a lot the efficiency of the whole task. And never neglect that a broader knowledge can really make a difference in our work. So from my side, that was it. I hope it was okay from you. So I'm open to questions now.
Are you hearing me? Okay. Now, questions to Dr. Roberta. I have one question. We could say that now a vehicle is a TI center on the roads, isn't it?
Yes.
Yeah. Hundreds or
Definitely.
tens of microprocessors are running on a vehicle. A question. Let me see. The audience don't have questions. Sometimes a problem on the very low level, like the analog block, may need some changes in the architecture level, in the system level.
Yes. And we hope that is going to be found right at the beginning. That's why we invested at the, let's say, the verification at a very bottom level, block level. It starts at the very beginning, and we can react then fast.
But you suppose you find in the pre-silicon phase, you find you find the problem in the low level. But sometimes this can happen only when the project is over with the may need a redesign of some systems.
Unfortunately, it happens sometimes.
Okay. And about software, you have a operating system on a car, on a vehicle.
So especially in this case, I didn't consider the software because I was considered more the highest amount of analog. So we may have only SPI, for example, not specifically microcontrollers. Only for this motor control applications, we do have software. And then, of course, the firmware should be represented here as well. And there's a direct integration, let's say, and also a specific Presilicon verification, including the firmware together with hardware.
Okay. Uh, a question, you showed that there is some expertise you expect to have in the people that work on this system. Do you find these technicians in the, or you need to train them when they are working?
It's very difficult to find. And yes, the technique is that we have to train them. Yes. So it's a process of creating awareness about what kind of special effects could have in
Okay.
the system level. Yes.
And another question, the audience, please, if you have questions, I don't see questions. Another question is, you are speaking as you have the domain of all the modules, the analog and module and high level, but sometimes you may need to use third party the components. And how can you work with some parts that are not known when you use them?
You mean the different, let's say, arrangement in a module level, just a part of a module level, for example?
Yes, for example, the battery may be furnished by a manufacturer that is not on your industry. Then
Okay, I understand.
you need some kind of arrangements or definition or specifications in order to put in your simulator.
Yes, that's true. So you do have a model, let's say, of the worst model possible, the most challenging, let's say, characteristics, electrical characteristics, and then we can put in the test benches and consider this under all corners and temperatures and so on. So usually we have representation with providers, also the external components, MOSFETs, and so on. We do have very specific characteristics for these components, and then we can adapt in our test benches.
Okay, and the uh, the industry have sometimes the specification procedure is compatible with your the language you use, or sometimes there is you need to have some kind of adjustments in order to have a precise specification?
I would say that within the automotive market, it's pretty much standardized the way we exchange information. So we don't need much adaptations.
Danielle Piovani, using a digital strategy with real number modeling for analog blocks is the worst strategy between a pure digital and AMS model. Digital strategy with real number modeling for analog blocks.
Yes, this is exactly what we use right now. So we do have the real number modeling. But we preserve, let's say, the analog, the digital signals in digital domains. So they are going to be represented as 0 ones. And whenever we have these digital signals in the analog macro, but the dependency of the signals to the, for example, the power supplies and to the input signals are represented now with the real modeling. And yes, it is the winning, let's say, choice, at least for us. I know that for much more complex systems with microprocessors, tons of ADCs or microprocessors itself, it can now compromise, let's say, the performance of the digital simulator even. But not in our case. We have the presence of analog design is very strong, so we don't have much. The part of the digital is somehow reduced or limited. So this is the perfect solution for us, let's say.
Okay. We don't have more questions. Then let me say that I am very happy to see you presenting to our community your experience in the very hot domain. We are seeing now automobiles with much much electronics for now the electrical vehicle and the self-driving. There is extremely powerful electronic that with the needed security will make a vehicle a very interesting domain.
Definitely, yes.
Danielle says thanks. Then I also would thank you very much for this very interesting presentation, and hope you have a very bright career.
Thank you.
Thank you very much.
It was my pleasure, really. Have a good time, you out. Thanks. Bye.
Okay. Bye-bye.